So let's see if we can get the share up and running. So first, I would like to apologize because this will not be the session throwing Java on Amazon Lambda, reducing cold start times from 11 seconds to 1, because it turns out that people are constantly developing. So instead, I will present to you the completely different talk, throwing Java on Amazon Lambda, reducing cold start times from 6 seconds to zero point 0.2. Because new versions of the JVM has been deployed and Amazon has upgraded their software and their hardware. So they shaved 5 seconds off it just by waiting, which I think is good, but we still have some work to do. So the first thing I want to do is talk about a bit about myself and why you might think I know one or two things about these. So my name is Raniz. I have a master's degree from Lund University. I eventually ended up at Sony after a few years working for different companies. And Sony sent me to Tokyo, where I educated them on Amazon Web Services and cloud services in general, and Amazon Web Services particularly. How to develop and what is available and what you can do with the cloud. I stayed there for 6 months, and then I returned to Sweden. I did work for a startup, and then I ended up at Factor 10, which is where I am at now. And we're a small consultancy firm that focus on business value and making sure that software actually contributes business value instead of being an obstacle. And as part of that, I am allowed to speak at conferences, which is why I'm here today. And apart from that, I am married with 2 kids, a daughter and a son, 5 and 3. I'm also a self-professed beer snob, which means that I generally don't drink lagers. I prefer more craft beer. I also brew my own beer, which is a fun pastime. And I also do triathlons, though I haven't done one in a few years, so I think it's time to do that. Otherwise, I will have to remove this piece of my slides, and that's too much job. So just do a triathlon. So let's back to the presentation then. I'm going to showcase this. We're going to write a simple Lambda function. And this Lambda function is, well, basically it's, we have our client on the left, which is, it could be a web service. We have our Lambda function in the center, and the client sends a user object to the Lambda function, and the Lambda function adds a unique ID and then stores it in the database, which in this case is Amazon DynamoDB. And I'm going to implement this using Spring Framework, because Spring Framework is something I've been working with for quite a long time, and I know it very well. You're probably familiar with it, because if you develop in Java, you probably used Spring at some time. If you don't, Spring is a framework for dependency injection or inversion of control, and it has modules for essentially anything you can think of. And of course, they also have a module for Amazon Lambda, which is called Cloud Function. It supports different runtimes, not only Amazon Lambda, but we're going to use it for Amazon Lambda. So to get an overview of what our Lambda is going to do, I have made a call graph. And this is, if we go from the left, we have Amazon Lambda, which calls into our function. And that call is intercepted or reaches Spring Cloud Function. And Spring Cloud Function, in turn, reaches the Spring context and asks it for our method handler, our function handler. And the context returns the handler, and then the Cloud Function calls the handle method on our handler. The handler gets the user object. It adds a unique ID, and then it calls the user repository, which also has been dependency injected by the Spring context. The user repository then issues a call to DynamoDB to store this in DynamoDB. And then DynamoDB returns, the user repository returns, the handler returns the cloud function, and Cloud Function tells Amazon Lambda to return the object to whoever called Lambda. And we're done. So let's take a few benchmarks on how this function performs. And you can see that it's all very, very speedy down here. It's sub 50 milliseconds. But this one stands out like a sore thumb. This is 6.5 seconds, and I don't like this one. So we're going to analyze this a bit further. But this is what we call a cold start. And cold starts is the entire reason of this talk. And before I go into what a cold start is, I want to talk about why we think cold starts might be a problem. And to do that, I have borrowed an image from the Amazon Lambda documentation. So this is I guess it's a web application of sorts. Let's say it's a single page application for a local theater. In the theater, you can have tickets, shows, and some information about the shows probably. We have 4 Lambda functions in this image, and it's these 4. We have an authorizer function that makes sure that all the requests that enter the system are authorized. And then we have 3 different Lambda functions for the various endpoints. So let's imagine it's a local theater, right? So there's only probably people from your town or nearby that visits this page, which means that it doesn't get any traffic during night when everyone is asleep. In this case, Amazon decides to shut down your Lambda functions because no one is using them. They don't want to waste the energy of having your Lambda functions running when no one is using them, so they shut them down. So someone wakes up in the morning, they grab their morning coffee, they want to watch some theater on Friday, so they visit your page. The first thing that happens is they load the page from, in this case, Amazon CloudFront, and then the single page application starts calling into the API. So the first thing that happens, they probably want to see the shows. So we're listing what shows it is. The single page application calls into the shows Lambda, but first it hits the Lambda authorizer because it needs to make sure that this request that we have is valid. And the Lambda authorizer has been shut down, so it's not running. So Amazon starts it up, and that takes 6.5 seconds. So the single page application makes a request, and 6.5 seconds later, Amazon has started your authorizer function and authorized the call. And then we reach the shows function, which also isn't running. So Amazon starts that, and that takes 6.5 seconds. And then we fetch all the shows and return that to the single page application. At this point, 13 seconds have passed since you loaded the page, and you still haven't seen any content. Now your page might show some information from the shows, but it needs more. It needs some information, right? So it makes another call. We hit the Lambda authorizer. This time it's warm, it's running. So this takes 50 milliseconds. You won't notice that. But next call goes to the info endpoint, and this is also not running. So it takes another 6.5 seconds to start up and then return. And you get some more information on the page. But then we need to see if there's any tickets available and what they cost, and if there are different kinds of tickets. So the application makes another call. We hit the authorizer, which again is warm, 50 milliseconds, won't notice. And then we hit the tickets Lambda, which of course isn't running. There's another 6.5 seconds. So when this returns, we have started up 4 Lambdas for 6.5 seconds each, which is 26 seconds of waiting. That's almost 30 seconds before your application. And if it's not a well-written application, it will wait for all these 4 calls before it starts showing anything. But by that time, I think your visitor has already decided to go visit another theater. You lost your client, you lost your sale. And we don't want this to happen. So let's analyze and try to figure out why the startup takes so much time. So if we go back to the call graph, we can see here that this is actually the warm case. When our application is running, this is how it works. But when the application is cold, we need to, because the user handler and the user repository, they aren't They doesn't exist yet. They aren't initialized. So we need to initialize those. And Spring does this for us, but it happens around here. So when the cloud function asks the context for the handler, the context isn't initialized. So the context initializes and creates the handler and the user repository, and then it returns it to the cloud function. And this takes some time. And let's benchmark and see how long this actually takes. So maybe the 6.5 second cold start we got when we benchmarked first could have been a fluke. It was bad luck. Maybe it's faster in general. So benchmarking cold starts might be harder than you think it is. You can't just start benchmarking the function because you will only get one. I mean, with the first benchmark, we did 200 benchmarks and we got one cold start. Now we want 200 cold starts and no warm. So what we do is you can update your Lambda function. If you update the configuration, what I do is I set an environment variable to a random number. Usually I just choose the iteration number, because that forces Amazon to shut down all your Lambdas and start them again, which means that they won't be running. We then wait for Amazon to tell us that the Lambda is ready, and then we publish a new version. And we wait for that version to be ready. And then we call that Lambda version 30 times simultaneously as quickly as possible to hopefully make Amazon start up multiple instances of your function. And then we collect all the log tails. And this is something you can do when you call Lambda. You can you can set an attribute on the call that you want the log, and the log will also contain some timings. And in these timings is an init iteration. And if there is an init iteration, it means it was a cold start. If there isn't one, the function was already warm. So we discard those that doesn't have an init iteration, and then we just repeat this until we have our measurements. And in this case, I want 200 measurements. So we repeat until we have 200 measurements. And let's look at those 200 measurements, and they look like this. So we can see here the best case is slightly more than 5 seconds, and the worst case is almost 7 seconds. So our 6.5 second was maybe not the average case. The average is closer to 6 seconds, but still pretty representative. So we're looking about at about 24 seconds for the single page application to start when no Lambdas are running. And you will also hit those 6 seconds if a lot of traffic happen. There's a traffic spike, and new functions need to be started, and people will wait. They won't probably hit the 24 seconds, but they will have to wait for 6 seconds. And 6 seconds is still a very long time. So what do we need to do? We need to figure out some sort of antifreeze for code. And what is antifreeze for code? I don't know. But let's analyze the situation and see what might be wrong. So when Spring starts up, this is essentially what happens. It scans your class path, looking for interesting classes that are annotated with annotations that Spring care about. And once it's scanned your complete class path, it figures out how everything fits together and how to wire everything up. And then it wires everything up and initializes it. Now, this seems kind of wasteful because our Lambda might be starting up thousands of times. And every single time we know that the class path is the same and the wiring is the same. So why do that on every startup? Well, that's how Spring does it. You can also switch frameworks. There's a different framework called Micronaut. Micronaut was released in 2018 by Graham Brosher, who is the author of Grails. And it works a bit differently. So according to the Micronaut way, this is a quote from their site, Micronaut can achieve a monumental leap in startup time. And that's exactly what we're after. So let's analyze what Micronaut does differently from Spring to achieve this monumental leap in startup time. Well, this is how Spring does it. Spring has its, when you compile your application, the compiler compiles it to bytecode. And then Spring, when you start it, Spring does its dependency injection. This is the class path scanning and wiring. And then some initialization happens in your code. This is, in this case, we open up a connection to DynamoDB. Micronaut does things a bit differently. So Micronaut uses the Java compiler annotation API, which means that whenever the compiler, when the Java compiler is compiling your code, if it sees an annotation that Micronaut has told it that it's interested in, it hands over control to Micronaut, and Micronaut can generate new code and analyze your code. And it does this during compilation to actually do the class path scanning and the wiring when you're compiling your application. So once we start it up, it should be as fast as if we had written everything hardwired or hard-coded, but we can still write it as if it's dependency injected. It is dependency injected. The dependency injection is just pre-configured when we compile. So this should be faster because there is no class path scanning, there is no wiring. There's a small amount of this done because you can still influence by environment variables or configuration, but most of it is already set up when we compile. And they're also very similar. Grails is written in Spring, so Micronaut is heavily inspired by Spring. You can tell by the way it works. It uses similar structures, it just uses different annotations. And most of the annotations that Micronaut use are the standardized from various Java standardization projects. Spring also support most of these, but they weren't around when Spring was created. So Spring tend to use their own and tend to default to their own annotations. But you can see here, we use introspected instead of component, we use inject instead of wired, and we extend an abstract class instead of implementing a interface for our handler. And it's the same story with the repository. We have singleton instead of component, and we use a slightly different way of getting the user table name from the configuration. We use property instead of value. So if we benchmark this, then do we see a monumental leap in startup time? No, we don't. We see a slight improvement in startup time, but we're still around 5.5 seconds, which is still too slow for me. There's still the issue of wait times. Micronaut didn't revolutionize this, so it can't be the dependency injection in runtime. It has to be something else. So what is the real problem here? Well, if we take a look at this image again, this doesn't actually tell the whole story. We need to put in another box here, and that box is this one. And this box says just-in-time compilation. And if we insert it to the previous image, it looks like this. So the just-in-time compilation is when the Java compiler compiles your code, it compiles it into bytecode, which is sort of an intermediate format that the Java runtime understands. But to actually execute this, it takes your bytecode and it turns it into proper machine code when your application starts up. And that's the just-in-time compilation. Or rather, it does it when you load the class, but when your application starts up, there's a lot of class loading happen. And this takes a lot of time, it turns out, especially on Lambda. So what we really want to achieve here is we want to start our application without doing all these just-in-time compilations. And last year, Amazon published or released a new function or a new feature of Amazon Lambda called Lambda Snap Start. And I think this is pretty ingenious because what they do is when you publish a new version of your function, they start your application, they let the application start, which is they let Java do the just-in-time compilation and your app does its initialization. And then they take a VM snapshot. And a snapshot is, if you've ever played emulation games, you know how you can save state. And if you die, you can just restore that state. That's exactly what they're doing. So they take a snapshot of your VM and they store it. And then once you need a new instance of your Lambda, to just restore that snapshot, which means that your function is already warm when they started. The just-in-time compilation happened sometime before, and we just resume a clone of the function from where the snapshot was taken. And we immediately can call the function without waiting for any initialization or just-in-time compilation. And this gets us pretty far. This gets us to slightly over a second. And as you can see here, the light blue is Micronaut and the light green is Spring Cloud function. It doesn't make a difference if we run on Micronaut or Spring Cloud. It's equally fast because it doesn't matter if you do the wiring in compile time or runtime, because all that is already done when we resume the function. Now, this is still a second. I think that's okay, but there are a few drawbacks. So one thing I found out when I was benchmarking this and toying around with Snapstart is that the first thing I did, I clicked the button or the checkbox in my Lambda, and I ran the benchmarks, and I got 4.5 seconds. I was quite underwhelming. So what I find out by talking to one of Amazon's architects is that you need to exercise your complete code path before the snapshot is taken. And you can do this by implementing an interface in a package called crack, which stands for Coordinated Resume and Checkpoint, I think. And you can implement a method that is executed just before the snapshot is taken. And in this method, you need to make sure that you call the functions, so all the classes are loaded, all the classes that are ever going to be used in your program are loaded and compiled. So you need to dry run your entire function at startup. And it can be difficult, but it's something you need to remember to do. And once I did that, we got the second runtime, around a second of cold start times. So that's a thing you need to do and something to remember when you're doing Snapstart. There's also another problem, and that is that this is LTS only. So I'm not sure if they've actually have released this for the latest Java version, which I think is Java 21, the latest LTS version. The documentation on the Java Snapstart, Lambda Snapstart page is confusing because it lists Java 11 and Java 17, and then it lists Java 11 and Java 21. So I'm not sure. But if, for example, a new release that is not long-term support has been released with cool features that you want to use, you have to wait until they reach long-term support. And you probably need to wait some more until Amazon supports that LTS version for Snapstart. So you're looking at maybe a few months after the latest LTS version that you can start using the features. And that might or might not be a problem depending on how much you like your modern Java and what features Java release. And one other thing. So this is a photograph from the World Endurance Championship. And the car on the left here, that's a Ferrari. It's a Ferrari 488 GTE. It has 490 horsepower. It weighs 1,260 kilos. That is a really fast car. But the car on the right is an Audi R18 e-tron Quattro. It has almost 1,000 horsepower and it weighs slightly less than 900 kilos. Watching these two on track is mind-blowing. The Audi completely destroys the Ferrari. It looks like a Ferrari overtaking a Fiat. So why settle with a Ferrari when you can have the Audi? I want the Audi. So what's an electric hybrid race car in terms of programming? Well, that might be Rust. Now, I like Rust. Rust is a completely different language from Java. Rust looks very different from Java, actually. So Rust, I'm not aware of any dependency injection frameworks in Rust. So this is how a Rust function looks. And this is mostly just see if we can improve, because I know that Rust is a very quick language, is known for being fast. So I rewrote the function in Rust and I benchmarked it. And that benchmark looks like this. So the red line down here, which is very consistent, by the way, is around 40 milliseconds. And if you remember the first benchmark I showed you on Java, Java, when it's warm, takes around 50 milliseconds. So Rust has faster cold start times than Java has warm times, which for me, I think that's pretty mind-blowing. So what about drawbacks then? Is there any drawbacks to Rust? Yeah, there might be. Depends on who you are. So Java is a completely, Rust is a completely different language from Java. If it's, I'm not sure if you can read this and understand it. It looks very differently. It works very differently. It has a completely different memory model, which might trip you up. It will probably trip you up when you start writing programs in Rust. I think that's a major hurdle to Rust adoption. But it's something you will get over. But it's something to keep in mind. It is very different. It is also in its infancy. So Rust is a fairly new language. I think the first release was in 2015. And it's, I mean, all languages are constantly evolving, but Rust more so. There are still some language features that are under development. There's a lot of things that are unstable. They can only use if you use a nightly version of Rust. And some applications and libraries require you to use the very unstable nightly versions of Rust, which might not be something you want to do with production code. There is also, especially compared to Java, nowhere near as many libraries as there is for Java. I mean, Java, the ecosystem in Java is immense. You can find a library for pretty much anything. There is a lot of libraries in Rust, but a lot of them are also in their infancy. They might not be battle tested. Some of them are unstable APIs, which change between versions. So you need to adapt and change how you use the library if you upgrade, which can be very annoying. So wasn't this about Java, by the way? Why am I talking about Rust? Well, the Rust detour is to prove a point, and that is that we can be extremely fast without snap start if we don't do just-in-time compilation. So Rust is a compiled language. It compiles down to bytecode. It compiles down to native machine code in the same way as C or C++ does. There is no virtual machine that needs to start up and just-in-time compile your code. It's straight up running. So can we achieve this with Java instead of Rust? And it turns out that we can. There is a project called GraalVM, and the original intention of GraalVM was to be self-hosted. And by self-hosted, when we talk about programming languages, a self-hosted language is a language that compiles itself. So C is self-hosted because the C compiler is written in C, or there isn't the C compiler, but GCC is written in C. I would guess that most of the other C compilers are also written in C. Rust is self-hosted. The Rust compiler is written in Rust. It originally was written in OCaml, I think, but nowadays it's written in Rust. Python is not a self-hosted programming language because the Python runtime is not written in Rust. It's written in C. Or on the JVM if you're using JPython. And Java is not a self-hosted language because the JVM is not written in Java. The goal of Graal was to write the JVM in Java and the Java compiler in Java. But that didn't really pan out the way they wanted to. It turns out that doing that is very hard. So nowadays, it's a JDK distribution based on OpenJDK that also bundles the Graal compiler. And the Graal compiler is what we're after. But I want to look at the things that Graal gives us more than that. So the Graal is a high-performance compiler, but it also comes with polyglot programming, which I think it's called libpolyglot, where you can actually mix languages in the JVM. So you can write different parts of your language in different parts of your program in different languages. You can, for example, mix Ruby and Java, or Python and Java, or JavaScript and Java. And your code won't really be aware that it's calling another language. It will just look at like any other Java function, even though it's implemented in JavaScript or Ruby or Python. And it also comes with the one on the top right here, AOT native image compilation. And that's what we want. That's what we're after. So it compiles Java applications ahead of time instead of just in time. And that produces native binaries that start up instantly and deliver peak performance with no warm-up time, the same way that C, C++, and Rust does it. We run the compiler, we get native code, and that just starts without any virtual machine, without any just-in-time compilation. So if we compare that to Micronaut and Spring running on the JVM, pardon, this is the previous image with the just-in-time compilation. When we use GraalVM, we move the just-in-time compilation to ahead-of-time compilation, and we move it from the runtime to the compile time, like this. And now we trade compile time for runtime efficiency. So you can see here, when we use Micronaut down here, we do the annotation processing, we do the compilation, the regular bytecode compilation, and then GraalVM takes over and does ahead-of-time compilation to native binaries. And once this application starts up, we just have to do the small amount of dependency injection that Micronaut does, and then an initialization. And we're up and running. So without the just-in-time compilation, how long does this take? Well, I've only done this with Micronaut because I don't want to try this with Spring. I'll get back to that later. But this is around 200 milliseconds. And I think this is as good as it gets. This is probably as far as we can push Java. And 200 milliseconds I think that's really good. I think it's not on par with Rust, but I think it's on par with Python, Ruby, TypeScript. Probably it might even be quicker than those three, because they do need to start a VM and they do need to do some sort of just-in-time compilation, especially because all three are interpreted languages. So Micronaut averages around 200 milliseconds, which as I said, I think we're done. We can't improve on this. So what's the drawbacks? Well, it turns out that just-in-time compilation is actually fairly quick. So when you move the compilation to ahead of time, you need to compile everything, every single class that might ever be used will have to be compiled ahead of time. Whereas when we do just-in-time compilation, we only compile the things that we actually need. So if you bring in a huge library with lots of classes and you only use two of them, in the just-in-time compilation case, you only compile those two classes. In the ahead-of-time compilation case, we have to compile all of those classes because we don't know whether or not they are used. And this has a significant impact on compile times. So on my laptop, compiling the Micronaut Lambda function takes a second. And we can add to that the just-in-time phase, which is around 6 seconds. So let's say 7 seconds for bytecode compilation and then just-in-time compilation. Whereas with GraalVM, if I compile the Micronaut Lambda on my laptop, it takes 2 minutes and 22 seconds. That is more than 2 minutes more that I have to sit and watch my computer just run its fans on max speed before I can deploy or run my tests or whatever I'm doing that needs to be compiled. You can offset this a bit, or you can mitigate this by, because it's a GraalVM is a Java compiler, right? So you can still run your code on the JVM. So what you can do is you can run your code on the JVM, you can run your tests, you can run your local development on the JVM and enjoy these quick compile times. And then when you're ready to deploy, you run the native compilation and you deploy. You need to make sure that you run your tests in native mode as well, though, because there are subtle differences between running on the JVM and running natively. Most of that is related to reflection, because reflection doesn't really exist without a running virtual machine. So GraalVM needs to be aware of the reflection, and it needs to add that metadata into your classes so it's available at runtime. So I actually have written test cases that work on JVM, but doesn't work in native mode. And you need to look out for that. So you really need to run your entire test suite in native mode as well. But you don't have to do that as often. Maybe just in your pipeline or as a sanity check before you push. So the next drawback then, well, that is tools. So all the tools you're used to, they don't work anymore. You can't use Visual VM to introspect or benchmark or inspect your running application because there is no VM for Visual VM to work with. You can't use the Java debugger to debug your native applications because they are now native applications, which means you need to use native debugger such as GDB. Now, if you're like me and you use JetBrains products like IntelliJ, IntelliJ does not support GDB. You would have to switch to a different editor. And in the JetBrains ecosystem, that is CLion. But CLion doesn't support Java. So you can either have an IDE that supports your language or one that supports your debugger. It's possible that this is solved by switching to Visual Studio Code, but I've never gotten along with VS Code, so I haven't actually tried that. But that might work better. I don't know how VS Code debugs native Java applications. So tooling is a problem, and there's also the issue of the framework or the magic that the framework provides. So Micronaut does a lot of configuring and telling Graal about metadata about your application, because Graal needs to know about reflection. It needs to know which classes should be initialized at compile time, because it will actually initialize some of your classes at compile time, and some of the statics will be initialized during compile time. And if it gets that wrong, compilation will fail, and you will get a very confusing error message. And Micronaut handles a lot of that for you. But as soon as you venture outside of what Micronaut knows about, you're completely on your own. And you need to supply this metadata to GraalVM, and that can be very frustrating because the error message you get aren't at all descriptive, and you might get a compiling error that says that a class somewhere deep down in a transient dependency pulled in by something you using was initialized where it shouldn't, and somehow you need to configure so that it's initialized at the correct time, and that might be by configuring a completely different class to be initialized during runtime. Those things can take a lot of time to debug, especially when they take 3 minutes to compile. So that's one thing to look out for. And the last thing is that Java one of the selling points of Java is write once, run anywhere, but that's not true anymore. Because now you're not producing bytecode anymore, which can be run by the JVM. You're producing native binaries, and native binaries are not portable. For example, if I compile a Graal application on my Arch Linux laptop, they absolutely will not run on an Arch Linux ARM laptop because I'm on a Intel processor. They might not even run on a Intel Debian machine because the versions of system libraries are different. They absolutely will not run on a Mac. And that could be a problem if you are deploying, say, you're developing on a Mac and you're deploying to Amazon Lambda, because now you need to compile x86 code for Amazon Linux on your Mac. Micronaut handles this by Docker, but you need to have emulation to target the different architecture, which might slow things down. Rosetta or whatever, yeah, the Mac translation layer might handle this well. And you get the inverse problem. If you're on Linux and you're targeting ARM lambdas, you need to have emulation up, and that will definitely be slow because there is no native support for emulating ARM on Linux x86. So it's something to consider. If you're distributing an application for multiple platforms, you now need to build a specific application for each architecture you are targeting. So honorable mentions, Quarkus, which is a dependency injection framework from Red Hat. It's similar to Micronaut in that it does ahead of time compilation, but it works a bit differently. I think I would say consider it personal preference if you like Quarkus or Micronaut better. And there's also Spring Native, which is an attempt, or I think it's fairly successful, to support native compilation with Graal with Spring. I haven't tried it. The last time I tried it, it wasn't stable. It has had a stable release, but I couldn't get it working. Hopefully it's better now, but I would go with Quarkus or Micronaut because Spring relies heavily on reflection, and reflection and GraalVM aren't really friends. So to end this talk, I want to leave you with this flowchart. And this is my flowchart for thawing your lambdas. So we start from the left, and the first thing we ask is this an issue? Because it might not be. Maybe this is a backend job that runs nightly and no one is really waiting for the result. We had that once. We only needed the result at 8 in the morning, it ran at 2 in the morning. It's not a problem. I think we even have 30 seconds of cold start time. No problem. We needed the result 6 hours later, so 30 seconds is fine. No need to spend time on optimizing this. But if it is a problem, are you willing to switch languages? If yes, then give Rust or Go a try, or maybe TypeScript, Python, or Ruby. I would suggest Rust or Go because they are faster, but TypeScript, Python, and Ruby have better performance than Java. But if you still want to stay on the JVM with Java, consider Micronaut or Quarkus and try GraalVM Native Image because that will probably work if you write your application in Micronaut or Quarkus. And if you rather would stay on whatever framework you're on, maybe Spring, well, then go give Snapstart a try because check the checkbox, make sure you dry run your application in the callback, and you will get good performance. You won't get the best performance. For that, you need to go to a different language or GraalVM, but Snapstart will get you pretty far. And that's it for me. So I would like to thank you for listening to me talking about thawing Java on Amazon Lambda, reducing cold start times from 6 seconds to 1. And if you have any questions, I am ready for them.
Yeah, thank you so much for your input. And yeah, if there are any further questions, just put them in the chat or unmute yourself. If that's not the case, we would go on with our break and we see each other back in around 15 minutes. So we start again at 1 p.m. There's one question in the chat. Raniz, if you would have a look.
Yes, the stability on Rust on Amazon Lambda. Rust is very stable on Amazon Lambda. As far as I know, there was a bit of issues with the the framework, or the library to call into or to set up Rust on Lambda before, but I'm fairly sure it's stabilized. It's been 2 years since I used that before, but I think Rust is very stable on Amazon Lambda. I have run production workloads. So the question is if Rust is ready for production workloads on Amazon Lambda, and I have run production workloads written in Rust on Amazon Lambda. So I would definitely say it's ready for production.